Welcome to lecture number 3 in the course on laser-matter interaction, and this is dedicated to the problem of the Krabbe-Kronig relations. Well, as I did already the first two lectures, I emphasized at the beginning of the lecture that when you talk about light-matter interaction, in order to be able to simplify the problem, you have to know approximations. And at the first and the second lecture, we made clear that the approximations that we would like to make is, first of all, we assume that light is a classical electromagnetic wave, but this has nothing to do with a light-matter interaction. But the approximations related to the light-matter interaction are, first, electric dipole approximation, assuming that the energy of light-matter interaction is defined by interaction of electric component of light with dipole moments in the medium. Second approximation is approximation of continuous medium, which says that in principle, instead of many dipoles, we can work with a macrodipole polarization. Third approximation aims to figure out the relation between the polarization which is induced in the medium by light and the electric field. And if you assume that this relation is linear, we will call it linear optical approximation. Fourth approximation is approximation of isotropic medium, and it says that whatever direction of the electric field of light is, it will always be parallel with the polarization that this electric field of light induces. And the same would be valid if we look at the vector of electrical displacement. And the final approximation was approximation of no dissipations, when we assumed that divergence of the Poynting vector is equal to 0. And it means there is no irreversible energy transfer from light to the medium, and as a result of this approximation, we could show that epsilon, epsilon that relates vector of electrical displacement and electric field, which for isotropic medium would be just a scalar, or chi, which relates polarization induced in a medium by the electric field of light and the electric field of light itself, then in both cases it would be a quantity which is equal to its complex conjugate. So it means it is a real number. So these approximations we took and we showed we can get a very simple model, intuitive model of light-matter interaction, which defines the optical properties, which describes the optical properties just with the help of single parameter. So in most of cases we will use epsilon. Why? Because epsilon very nicely relates to the refraction coefficient, something that we can measure experimentally, measuring speed of light in a medium. And as I promised at the first lectures, the goal of the whole course would be to look at all these approximations one after another and to emphasize what physics we overlook by accepting each of these approximations. And now the first approximation to treat today is the approximation of no dissipations. Now I will focus now on the physics which we overlook by accepting no dissipations. Well, already at the last lecture I showed that you switch dissipations on, the refraction coefficient becomes a complex number. It acquires an imaginary part. And the physical interpretation of this imaginary part is, as you could see, it is practically a quantity that characterizes the decay of the strength of the electric field of light in a medium. So basically it is made to emphasize, to characterize absorption. Which is obvious conclusion at the end. We switch dissipations on and we obtain we see that the medium has an absorption. Obviously, the absorption is is a result of irreversible energy transfer from light to matter. And here at the accepting non-dissipative approximation, people may complain that non-dissipative approximation has nothing to do with the reality. There is always absorption. However, the goal of my lecture today is to show that if you assume that there is no absorption at the specific wavelengths, you hardly lose anything. Basically, if you know, so what I wanted to show you, that if you know the real part of the refractive coefficient, the spectrum of the real part of the refractive coefficient, you will be able to calculate the spectrum of the imaginary part. And the same is valid if you look at the real and imaginary part of optical susceptibility, or real and imaginary part of dielectric permittivity. So if you know one, you can calculate another one. And the tool that allows you to do this transition and this transition is called the Kramers-Kronig relations. Well, let's start with the Kramers-Kronig relations. And if you look in the books on electrodynamics, you will find that the proof for these relations is practically in every book on electrodynamics, and this proof is very lengthy, and it is a lot of mathematics. And what people overlook very often is that there is a very important physical principle behind, and as a result of it, it's not very obvious how to apply Kramers-Kronig relations. And these are the questions I would like to treat during the lecture today. Let me remind you how we derive Kramers-Kronig relations. What would be the derivations? The derivation that when you look at the book on electrodynamics. The derivation starts with stating that we have a certain force F acting in the space point r prime and a time point t prime, and this force causes some response of the medium at the space points r and time point t. It is very important for Kramers-Kronig relations, but very often people overlook this fact, that you begin your proof with the statement that force times response should give you the energy of interaction. Another thing which we assume here is that if you want to calculate the response, you can follow the following expression. Where G characterizes the property of the medium. Then what we can do, we can simplify problem a little bit. We can assume that this is a local problem. So basically, we analyze a response in a specific point in space, and as a result of action of this force on this specific point. So basically, we neglect dependence on the coordinates. So the point in which we measure response is exactly the point where we apply force. Then this equation becomes easier. because we only have now the dependence on time. And since force and response are defined such that the product gives me the energy of interaction, it is reasonable to state that if time at which we measure response is less than the time at which we apply force, then there is no response. Obviously, which we would call causality. And if time at which we measure response is larger or equal to the time at which we measure the response, then of course the response can be non-zero. We can rewrite this expression slightly differently, where we put here just minus, and here minus, here minus, and here we state that if t minus t1 is less than 0, the property is 0, and if t minus t prime is more or equal to 0, the property is allowed to be non-zero. Once again, we call it causality. So something very logical. So because the response is a result of force acting on the system, we cannot expect any response before the force had actual act. So then, in the definition, in the formal derivation of the Kramers-Kronig relations, what people do, they make Fourier transform. So from this definition of the relation between the force and the response through the property in time domain, we will derive another equation which relates force and response in the frequency domain. For this, we write Fourier transform. Okay, so these are three expressions which make sure that for force, response, and the property, we make transition from time domain to the frequency domain. And then, using these expressions, we write expression for the property in the frequency domain. So using Fabini's theorem, we change the order of differentiation with respect to t and t prime. And the result that we get will be like this. And now if you look at this part and at this part, you can recognize this is nothing else but Fourier transform of the property times Fourier transform of the force. So this very lengthy derivation was needed to show that also in the frequency domain, response of a medium to a force at the frequency omega, and the response of a medium would be at the very same frequency, satisfies this linear relation with g at omega as a property at this frequency. Next step in the derivation, in the conventional derivation of the Kramnik-Kronig relation, is a bit weird, because then, as you can see in the books, people start to work with complex frequency. And now it is the moment to benefit from the fact that we have a causality here. Then what we also use is the Cauchy theorem. And analyze the behavior, analyze this integral on the complex plane of frequencies omega 1, omega 2. Since there is a causality here, then in order to make sure that this integral converges, we can only integrate over the positive semicircle here, semicircle, excluding the pole here at omega 0, and applying this Cauchy theorem to this semicircle, we will find that, well, also assuming, by the way, that if you calculate the limit of g at very large frequencies, then it would be 0. It's just an assumption. If it is not the case, it will introduce a small correction to the final result. But then, using this integral, add the fact that if you integrate over this small semicircle, you will get here, this is the radius. If this radius tends to 0, then this is equal minus p I this. So finally, if you bring everything together, and you assume that G has real and imaginary part, you will find an expression for real part by principal value, so it means the integration excludes the pole here, excludes point where omega prime is equal to omega. And here minus by principal value of the integral again. And this is what you would find in textbooks as the Kramers-Kronig relations. So from these Kramers-Kronig relations, you will see that in particular people derive that for optical susceptibility, for real part of optical susceptibility, we can find this expression. And for imaginary part of optical susceptibility, we will get this expression. What is important here is that if you know the integral over the spectrum of chi double prime, which is imaginary part of optical susceptibility, from zero frequency to the infinity, you can calculate the spectrum of the real part. And the other way around, if you know the spectrum of the real part of optical susceptibility from zero here, not minus infinity, to plus infinity, you will be able to calculate spectrum of the imaginary part of optical susceptibility. Just to let you see that this is very powerful expression, and well, I wouldn't confuse you any longer. I also found it very long and very difficult derivation with little physics behind, because the only physics behind was causality principle. My personal opinion, I don't believe that theorems in physics are derived like this. There must be something more simple, more intuitive, that people would realize, I don't know, sitting under the tree. What can it be? Well, let me repeat now the general logic, but skipping these very lengthy derivations, which you can find, well, first of all in the lecture notes, and secondly in every book on electrodynamics. But now I would like to focus on things which normally escape attention of people, and as a result of it, this is sometimes a very interesting discussion whether we can apply to the Kramers-Kronig relations to a particular property or not. As I promised, now intuitive derivation of a similar principle. I have a force that acts at time t prime. I have response at time t. Then the property, well, let me make it more simple now, less general like in a conventional derivation. The property that relates response at time t and force at time t prime is property h large, or h small, sorry. H small, that of course depends on t and t prime. Then, if t is less than t prime, this property must be equal to 0. This is what we call causality. We don't expect any response before the force. And this, as I said, the only physical statements in this derivation. Next. Well, let's assume that t prime is simply 0. It would be more convenient. And then let me pay attention to the fact that in principle I am allowed to write this property function in terms of two parts, two ratios. If you look at this term, we will call it odd term, and look at this term, we will call it even term, meaning that if this is odd term, and if you change the direction of time, the term will change sign. And this is if this is the even term, and if you change the direction of time, it will not have any effect on the function. Now, you notice that these two terms must be such that ht for t less than 0 must be equal to 0. That's what we call causality. So if you plot the dependence of the property as a function of time, it should be 0 here, and here it may have some dependence. But it means that if you look at the negative times, the sum of these two functions should give me 0. So it means that I can rewrite this in a slightly different form. Where odd time times special function signum as a function of time plus again odd function, where basically substitution and the even function is signum time odd function time, where signum is -1 for negative times and +1 for 0 and positive times. Now, as previously, I only have to make a transition between time domain to frequency domain, calculate Fourier transform, and if you calculate Fourier transform for even part of this function, h small, you will see then, since it is an even part, the even part, if you expand the exponent and represent this in terms of cosinus and sinus, this is even part, and since you have to integrate afterwards, even part plus even function times even function will give you non-zero integral, but even function times odd function will give you 0 after the integration. So what you will get at the end, you will get here that even part in the frequency domain would be a real number. Then you repeat the very same thing for the odd part. And here we have similar situation with a slight difference. It is an odd part. If you multiply it by, it is an odd function. If you multiply it by even function and take an integral, you will get 0. But if you take odd function and multiply it by another odd function and take integral from minus infinity to plus infinity, you are allowed to get non-zero. But it also means, since we have imaginary unit here, that we will get imaginary number. And now we reached very important conclusion. If you talk about even parts of the response function, even in time, it will give you real number in the frequency domain. If you talk about odd response function in time domain, it will correspond to imaginary number in the frequency domain. Are these quantities mutually independent? Of course not. Because, as I stated earlier, if you have causality, it means that in time domain, even part is a product of odd part plus times this function sigma. So in time domain, these two functions are not mutually independent. That it also means that the frequency domain, they Fourier transforms are mutually independent, and it happens such that in one case we are talking about purely real part of susceptibility, and in another case we talk about purely imaginary part of susceptibility. It basically shows that real and imaginary part of susceptibility are not mutually independent. And this is the only idea behind the derivation of the Kramers-Kronig ratio. So if you like, we can go a little further and we can apply Fourier transform to this expression, and if you apply Fourier transform to this expression, you will get something that looks very similar to the Kramers-Kronig relations. So just Fourier transform of this function signum minus infinity plus infinity is signum t exponential minus e omega t dt, and it is equal to 2I. And if you search for a transform of even function, it would be minus infinity plus infinity signum h odd as a function of time exponent minus t dt is equal to the answer is minus infinity plus infinity So here we apply convolution theorem to come from to get from this stage to this stage, and eventually, so we simply have to substitute here Fourier transform of this function. And this, as we showed above, is 2I if you compare this, while here, of course, we have different limits of integration compared to final expression here. But the main features you will recognize. Here we have even part on the left, odd part under the integral. 2, and even this difference, which will be modified when you change the limits of integration, y. That's the details you can look in the lecture notes in the original, in the conventional derivation of the Kramers-Kronig relations. But then the main principle behind that even part in the of the response in the frequency domain and the odd part of the response function in the frequency domain are not mutually independent. Basically, it shows that if you have a property that connects force and response, then we have, if you know the real part of this property, the frequency domain, we can calculate the spectrum of the imaginary part and other way around. So basically, when we assume non-dissipative approximation, and if you know all the information about refraction coefficient, basically we do not lose much because we can calculate the spectrum of absorption coefficient using the Kramers-Kronig relations. And now let me emphasize once again, the only physical principle behind this derivation was the principle of causality. The principle that if you talk about light-matter interaction, that if we act with a force like electric field on the medium, the response, like polarization, can be observed only at a later time scale and not earlier. But now I have a question for you. You will find that people apply Kramers-Kronig ratio to coefficient chi, which relates polarization and electric field of light. But then, in principle, you can also write this expression. And D is also sort of response. Why don't we apply Kramnik-Kronig relations to epsilon? Here, we must be very careful. As I emphasized at the very beginning of the derivation, causality can be applied only to the force and the response defined such that the product gives me the energy of interaction. If this is not the case, we cannot use the principle of causality. And in order to demonstrate this better, we can try to see what's going on, what would happen if we apply the principle, if we try to apply the Kramnik-Kronig relations to quantity epsilon. So imagine that I'm now talking about this product. And try to apply the property, the law which is defined by the Kramnik-Kronig relations to epsilon. If you calculate this, so in particular, for instance, if you calculate energy behind this product, and then you write D, write this integral, calculate this integral, and what you will get is 1 over 2 epsilon 0 epsilon E square, basically applying this equation. And then here you can also write down two terms. Because D is also epsilon 0 EP. Look what we have here. This is indeed the energy of light-matter interaction. But this is the energy of electromagnetic wave itself. It will also be present in the vacuum, for instance. Now, imagine that I take a very short laser pulse, very short light pulse, like shown on the slide. In time domain, this laser pulse will look like this. If you make Fourier transform, it will have a continuous spectrum. Now, I remove one frequency. Imagine that I had this pulse, and at time t prime, I just removed one frequency from the spectrum. This frequency in time domain will look as a sinus. And the narrower this gap which I remove from the spectrum, the longer the sinus will extend to plus and to minus. So basically, if this is infinitely narrow, if this is the delta function, the sinus will be defined from minus infinity to plus infinity. What does it mean? Well, it means that I have to draw this sinus in time domain and subtract this from this original form. What it will give me the graph that is shown at the bottom of the slide, where next to the oscillations during the laser pulse, I will also get oscillations at the positive time scale, out of phase with that sinus that I subtracted from the original signal. But what is the most troubling is the fact that also in the negative time domain, I will get this tail. Does it mean that I changed the past? Of course not. Because, well, you didn't have a removing frequency at this particular time point. it didn't have any effect on interactions, on light-matter interaction. So basically, you are allowed to remove any frequencies from the spectrum here. It will, well, since we're talking about Fourier series, it will generate some electric field in the past, but this electric field will not be associated with any interaction. Basically, it will not contradict anything. But if you want to apply the Kramers-Kronig ratio, you will be allowed to do this with respect to the quantity chi. And here we have a real force, real response, and the force and the response will only be possible after the action of the force or during the action of the force, but not before this. And applying causality principle to chi, we will derive Kramers-Kronig ratio. In short, since there is no interaction associated with this term, we are not allowed to apply Kramers-Kronig ratio to epsilon. We must apply it to chi and then calculate epsilon using well-known expression. Another very important statement is that if you measure a spectrum and imagine that we measure a certain part of the spectrum, that the refraction coefficient is not, that the absorption coefficient is 0, but somehow refraction coefficient is not equal to 1. It would mean that there is absorption somewhere. The refraction coefficient cannot be equal, cannot be less than 1 or more than 1 if light doesn't interact with the medium. There must be an interaction. There is not necessarily an energy transfer from light to matter, but there must be a fact of interaction. And if n refraction coefficient is not equal to 1, applying Kramers-Kronig ratio, you can find that somewhere at different wavelengths, at different frequencies of light, there must be a strong absorption. Why? This is because of the Kramers-Kronig relations, and at the end, due to the causality principle. Well, that brings me to the take-home message. The Kramers-Kronig relations show that the real and imaginary parts of the optical susceptibility are mutually dependent. It means that the refraction coefficient and absorption coefficients are mutually dependent too in spectral domain. And using the Kramers-Kronig relations for the optical susceptibility, one can derive similar equations for the spectra of absorption and refraction coefficients. It basically summarizes the point 1 and point 2. And if refraction coefficient at certain frequency is not equal to 1, somewhere in the spectrum the absorption is not 0. And in fact, accepting non-dissipative approximation at one particular wavelength, we do not overlook much of physics. We still can talk about interaction of light and matter if refraction coefficient is not equal to 1. Absorption coefficient can be 0, even if there is interaction of light and matter. At this, I would like to conclude. Thank you very much.